Okay, so today we're going to discuss, we're going to talk about constraint satisfaction problems. Okay, I will call it CSP for the entire lecture. It's just the abbreviation for constraint satisfaction problems. Okay, so we're going to talk about slightly different problem. In all the previous lectures, we have been talking about search problems, right? Uninformed search, then informed search. We basically assume that we know the environment or we know the world state, right? In some cases, we also assume that we know that how the world is going to react to the programs that we wrote, such as, Pac-Man, robot, discussions that we had, right? Traveling Romania problem. And we have been talking about, a problem in which we have to find the solution using the least cost path. We knew where the goal is. We created an entire tree, we expanded the tree, right? And then we implemented several different algorithms to get to the goal state, right? And then the output of the algorithms was that we find out the least cost solution, right? Least cost path. The path that costs us the least, I should say, that is the least cost path, right? So in all those search problems, the most important thing for us was basically the path or the solution, or basically we knew the goal and then how to get to the goal. So most of those problems, actually all of those problems were deterministic problems where we said that, we knew the state of the world, we knew where the goal is, we'll just simply have to get to that goal state in a most efficient way, right? With the least cost path, with the less time complexity, less space complexity. Okay, those were the algorithms that we have covered. Today, we're going to talk about something, it's still a specialized case of a search algorithm. Constraint satisfaction problems is still a specialized case of search algorithms, but they are much more general purpose algorithms. They are applied in a much more wider spectrum of real world problems. We're going to talk about a couple of those today. And they are applicable to many real world case scenarios that they have already solved those problems. And I will provide a few examples, and I'll provide explanation of, how constraint satisfaction problems are applied, what sort of algorithm is applied in the backend, and how it solves the problems, real world problems. Okay, so we're going to discuss basically constraint satisfaction problems as a general purpose algorithm, how we basically generate a problem structure. And in this case, basically, we will do how we will see how we will do the problem, identify the problem structure, and then how we decompose the problem that is different from uninformed and informed search algorithms. Okay, and we will talk about what local search algorithm that is implemented behind constraint satisfaction problems. Okay, so as I said, constraint satisfaction problems are specialized problems, but in addition to those, they're also general class problems. And we will see what do we mean by general class problems. Okay, the most important things in search algorithms that we have been talking about was basically quite a few things, right? State space, action space, start state, successor function, and goal state, right? The 5 tuple information. So in most of our previous, examples, algorithms that we have been talking about, we assumed that the world is known. We assumed that, the environment basically is known. Environment is mostly deterministic. But what we didn't know was basically we also knew about the state of the environment, right? State was kind of a black box, right? Meaning like a state, it can be an XY position for Pac-Man, right? A latitude, longitude value of an actual robot, right? Latitude, longitude value for yourself standing in the city of Arad, right? So the state, basically state space, was considered as a black box. It can be anything, right? So, and then we had the start state, we had the terminal state. So, and then what we had was in our successor function. successor function provided us basically the ability to take an action and get to a new state, right? So we basically, we made certain assumptions about the world. There is a single agent, right? And the actions are basically determined without worrying about the agent's movements, right? So what we have in here in the constraint satisfaction problems, first of all, we said that we are now basically going to assume that the environment is stochastic. So the biggest difference between CSPs and the other search algorithms that we have covered is that the goal is not the important thing in here. The path is not the important thing in here in the CSPs. In search algorithms, what we have mostly been doing is we have been planning, right? Planning, looking at the making a complete plan by being a mastermind Pac-Man or smart agent, or we have been pathing, right? Like we have been searching for a path that is the least cost to the goal state. Here, in most of these, because the environment is stochastic, we don't know where the goal is. So we have no idea where the goal is. We have to identify where the goal is that is well informed. So it's kind of an identification problem that we're going to solve. So we have no idea where in the tree the goal is. We will have to step by step take actions and identify where actually our goal is, identify the goal, and then make sure that that goal is well informed. By well informed means it's a better goal than other possible solutions. In constraint satisfaction problems, we're going to have more than one solutions because we don't know where the goal is, right? In other problems, we said that here are some possible leaf nodes or some nodes that are the goal states, and we will just have to get to that goal with the least cost path, right? So here we're not doing the pathing, we're not doing planning. We are simply recursively or iteratively, taking actions, taking steps, and having some constraints, some limitations, okay, some constraints that we have to follow, that we have to make sure that we are satisfying those constraints as we take the actions. And then we have to identify the goal that is well informed, okay? So constraint satisfaction problems, first of all, it is a special subset of search problems, okay? So right now, before we had the successor function where it would just give us the state and action pair, right? So that we could have taken an action from one state and get to another state, right? That was the successor function. In here, what we do is, as I just said, we take the action and then we have to ensure that we are not violating any constraint that we have to be in. Because we don't have the goal, right? We have to identify the goal by satisfying all the possible constraints that we have to face. So each of our problem that we are going to solve in here is going to be based on some sort of constraints, okay? And I'll talk to you about, what those constraints are or what the constraints can be. Okay, so in basically the state, in constraint satisfaction problems is basically identified by two main things: a set of variables, xi, because we can have multiple variables now, okay? Multiple variables, and then we have a domain. So we assign values to certain variables, and at each step, we ensure that we assign the values to a variable in such a way that no constraint that we have in our problem is violated, okay? Remember, we said that in A star that if we have an inconsistent heuristic, we might violate, or we might, end up being in a situation that A star is not even going to be optimal. So we had to make sure that our heuristic function is the most optimal, right? Here, what we have to do is we have to be sure that we are consistent at every step by making sure that we are satisfying all the constraints that we have in hand before we solve the problem, okay? So there are two main and important things in CSPs that we will have to remember is that we have certain variables in our problem, and we have a domain or a set of values that each variable can take. And we assign some values to some variables, like to some variables that we choose to assign, and we create a tree, and then we make sure that if that assignment is consistent or not. And we will talk about how we identify the goal using by assigning values to variables and by satisfying all the constraints. So the goal test in CSP basically is the set of constraints specifying allowable combinations of values, okay, for subsets of variables, which is what I just mentioned. So basically the beauty of constraint satisfaction problems is it's language independent. So in our previous problems, we have been writing Python code, right? So we've been typing and programming the solutions using Python code. CSPs are more, as I said, general purpose. We can simply provide a formal representation language. So this is going to be independent of the programming language that we have. You can choose JavaScript, PHP, C++, Python, any programming language. You can solve a CSP in any of the programming languages that we have. Now, if you see that using Python, if you don't have TensorFlow, Keras, or some of those packages, you will not be able to solve a identification problem or classification problem in images. Okay, because or it might be very, very difficult for you to solve the problem. Here, you can solve that in any language because we have simple constraints, assignments to variables, as some data structures that we are going to use, and we are going to provide a simple example, formal representation. Okay, so it basically allows useful general purpose algorithms with much more power than standard search algorithms. And let's talk about one of the most famous problems that has been solved using constraint satisfaction problems, map coloring. How do we color the map? Something like this. Is there any Australian sitting in this classroom? No? Okay, good. Because then the way we did the states, identified the states, it may be wrong, but if there's no Australian, there's no issue. I'm recording it, so I have to apologize if the division between the territories is not correct. So that's okay, right? So what we do is, this is one of the most famous problems that has been solved by using constraint satisfaction problems. We have a map. We have a map of Australia, and we have to color the map or color the territories or counties or states using different colors by satisfying some constraints. So let's talk about what those constraints are. First of all, let's talk about the variables and domains that we have, right? A set of values, a set of variables. So the set of variables can be these different states, right? Western Australia, Northern Territory, South Australia, Queensland, et cetera, the top left line. So these are the variables that we have, right? And then the assignments or the values that they can have assigned are going to be different colors, right? So we have the domain DI with 3 different colors, right? Red, green, blue. Each state can be assigned one of these colors. All right. Then we have constraints. So now we have the variables and we have the domain, right? Set of variables and a domain DI. Okay, great. But we have to assign colors in such a way that they have to satisfy some constraints. What can be those constraints? 2 different types of constraints. Implicit constraints. Okay. One implicit constraint in map coloring problem is that no 2 adjacent states can have the same color. Okay, so the 2 states that are actually bordering each other, they're not going to have the same color. So implicit constraint. The first line, for example, Western Australia is not equal to Northern Territory. That unequal sign or inequality between the 2 states, this is called the implicit constraint. That indicates that WA, Western Australia, is not equal to Northern Territory, meaning Western Australia cannot have the same color as of Northern Territory because they're adjacent to each other. That's the implicit constraint. Then we have some explicit constraints. That's more helpful from the programming perspective. Explicit constraints basically are still the implicit constraints, but with much more information, much more knowledge embedded. Now you see here, the first line, you say Western Australia is not equal to Northern Territory, if the language allows this, right? Or we can say we have Western Australia, we have Northern Territory, and they can have this sort of color. this sort of color combination: red, green, red, blue, green, red, green, blue, blue, red, blue, green, etc., etc. So we kind of do the enumeration, right? We enumerate all the possible combinations and we put that as an explicit constraint. Okay, please remember, because this is going to be very helpful for you for homework too. Right. Yes. Right. So explicit constraints embed much more knowledge than the implicit constraints, because you see, like the two lines, the second line has much more information about the problem than the first line, right? Because you see, like, from a programming perspective, you can say red, green, and you can assign like either 0, 1, 2 to red, green, blue or something. And then you can say, two states can have these colors because they're adjacent. Sounds good? We also have a Tasmania as an island, but we will talk about it because it's an island. It's not, bordering anything. But what we will assume is that Tasmania basically is nearest to Victoria. So we're going to make sure that these two don't have the same color. Okay. All right. So implicit constraints and explicit constraints. And then the solution to our constraint satisfaction problem is basically the assignment, satisfying all the constraints. So what constraint do we have in this map coloring problem? One. No two adjacent states are going to have the same color, right? And then a solution that we may be able to find using, some sort of algorithm that we're going to talk about soon is that, each state is going to have a color, and by making sure that none of the adjacent states are going to have the same. So that's our solution. See, we don't have the goal. We have identified the goal that is well informed. All right. So let's talk about another problem, the 4 queens problem. Basically, this is also a very famous, AI related problem that the CSPs basically can solve. What you do is you put the queens in certain, squares in the board that no queen is threatening another queen. So this is like a 4x4 board, and then you have 4 queens. So one constraint in this is that, if there are 2 or more queens in the same column, same row, or the same diagonal, that's violating a constraint, right? Because if they're either in the same row or same column or the same diagonal, then they can kill each other. They're threatening each other. Something like that. You see here? We have to place them in such a way, in such an order, that none of those queens are threatening any other queen. So this is just very simple 4x4 queen problem. One possible solution, or 2 possible solutions is, the first possible solution that we can find out is that I1 there's something wrong with the pen. I1 up to N, no, I from 1 to N, and there are queens, right? Using this formula, we say that N equals 4, right? Because we have 4 queens. So at one solution could be that each square, there is a square, and we can identify the domain. So the domain in this case can be 0, 1, right? If a square has the value 0, then that means there's no queen on it. It doesn't have a queen. If it has a value of 1, then that means there is a queen on it, right? Simple domain. Check for each square. Now, each square, like Q, like, here, 1, 2, 3, 4, and then 1, 2, 3, 4, right? 4 columns and 4 rows, right? We can say that, we can say that for each square in this board, if the sum of the queens is equal to the number of queens, then that means all the queens are on the board, right? That can be one solution. But does it tell us that it is satisfying the constraint? No, right? So basically, this solution is not very informative because it doesn't tell us, even though it tells us that there are the number of queens are there, but it's not telling us that if they are placed in the locations that are not threatened. What we can do is we can check, we can come up with this kind of solution. Q11, which is this, and then Q21 can have explicit constraints. Now remember, Q11, which is this, these two squares, they can have no queen, right? Q11 can have a queen, but Q21 shouldn't have a queen. Q11 may not have a queen, and Q21 can have a queen, right? You can have solutions like this, and then you can come up with all the explicit constraints, right? Nathan is smiling because there is an issue, but I'll talk about it very, very soon. Okay, so there is a guy, I think of a few months ago, I read an article. This guy, he was a postdoc at Harvard University, and I think he's now an assistant professor at Harvard because he identified this formula so we just talked about 4x4, right? 4x4, pretty small. We can still come up with a pretty quick solution. So using constraint satisfaction problems, we can go up to 25 queen issue or even up to 100 queen issue. But above 100, nobody has been able to estimate what are the different possible ways that the queens can be placed on the board that should satisfy all the constraints. So this can be applicable to many, bigger or larger real world problems like big data kind of problems. So he came up with this formula after a very, very large number of simulations. I don't exactly remember this number. It was either 481 or 418 or 4.81, something like that, times n power n. Okay, so even if n is a million, he said that if we know the n, and if it's an n by n queen problem, there are that many possible ways that different queens can be placed on the board so that no queen will, threaten each other. So this is actually a pretty good advancement in this area, that he's basically claimed that this is the most accurate possible estimation of the number of ways the queens can be placed. Because, using normal computational resources, it's not possible to do it for a very, very large number, n, because you see there is an exponent. Suppose if n was 1,000, right? So nobody has been able to do it, but that guy actually has done it and showed that this formula basically is the most accurate possible estimate. Most accurate possible estimate. Approximately, we might be able to, if we do check, there might be. So that number 0.481, that's not the exact number that I remember. It was a few months ago. There is a number there that is the correct one, and it's actually an estimate. It might be a one low or one higher possible way. It's the most accurate possible estimate. So using that formula, you can come up with an estimate saying that there are these many possible number of solutions. Okay, so what we can do is we can look at this. All right, so and that stops working for some reason. So let's say we have 1, 2, 3, 4, 1, 2, 3, 4. Let's say we have 5 queen problem, 5 by 5. Okay, so Q1, Q2, Q3, Q4, Q5, and then columns A, B, C, D, E. Right. So now you see here the constraint. Let me just pull up this jar file. There's a really interesting jar file. Oh, how can I view? Is there view? Zoom? Yep. Where is okay. What does it say? Drag the right mouse up button to zoom in. Point 143. Not 0.418. That's pretty high. 0.143. What does it say? Drag the right mouse. Oh. Button up to zoom in and down to zoom in. Oh, I wish. Oh. All right. So what we see is, there are 5 cells, 5 columns, right? And then there are 5 queens, right? Now you see if we go to solve and we say auto, what is that? What just happened? I wanted to show you where. Oh. No, I shouldn't have done this. Okay, no point. Let me just open this again. It's a very interesting tool that I found online. 5 queen problem, load, and then solve. Okay, this is not bad, at least. So if we say auto solve, then you see it will start basically with every possible arc. Every possible arc, because each square, there is a square that basically has a connection with another square, right? So we have to check. So each square, basically A and B is connected because there are the columns adjacent to each other, right? So it has to check all possible solutions. And what we're doing is the CSP iteratively checks, what if there is a queen on one square and if there is a queen on the other square that is adjacent to each other. If they are, then it recursively, iteratively deletes, removes the assignments, removes the values. For example, saying like, if there is a queen on A1, then B1 cannot have a queen. So if it assigns the value 1 to A, then it will remove the value from 1 from B, because it is not possible. So iteratively, it keeps checking every single possible assignment, and then it keeps removing the values that basically violate the constraint. So at the end, what we do is we find this combination. You see A1. Come on, please. A1, B4, A1, B4, C2, D5, and E3, right? A1, B4. So it does this. So we have, so this is A, like this, C, B, C, D, E, 1, 2, 3, 4, 5, right? A1, so there is it placed the queen here, and then it placed the queen at B4, C was 3, probably, right? No. C2. C was 2, and D was 5, and E was 3. See, this is one possible solution. None of the coins are basically threatening each other. So remember, there is no, so CSPs find one of the many possible solutions. This is one of the possible solutions that CSP has found. Okay, so let's talk about another problem that we have already talked about. Lecture number 2, week 1, crypt arithmetic example. Okay, where the sum of two words is equal to a third word, but in that case, in that case, there were variables. Basically, each letter was a variable, but then there were some carryovers too. If you remember, y equals 1 plus w, or blah, 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 blah. So we had some carryovers, x1, x2, x3. The domain can be the numbers assigned, right? The digits. And what was the constraint, by the way, if you guys remember? The same number, right? So one simple constraint can be that all the words, all the letters, they will have to be different. And then we have some more constraints. So this cryptarithmetic example can also be solved using constraint satisfaction problems. So we will have to create constraint graphs. So let's talk about, different varieties of CSPs, okay, and varieties of constraints that. Okay, constraint satisfaction problems can be of discrete variables and continuous variables. So discrete variables, for discrete variables, just like letters, coins, we know that there are 5 coins or 4 coins. These are discrete letters. Okay, so we can have basically discrete variables. In that case, basically the complexity is exponential. We'll talk about, very briefly, we'll talk about how we can reduce the time complexity, okay, improve the time complexity. Then we can have Boolean constraints, CSPs too, just like 1, 0, true, false, yes, no, etc., etc. We can have those kinds too. Then we have infinite domains, like continuous numbers, right? We can have continuous numbers, such as job scheduling. Well, I'll show you guys what job scheduling, how this is, solved using CSPs. In that, there are basically job start times and end times are basically infinite. It can be any time, right? So we can have those. Then we can have continuous variables, such as the observations from Hubble telescope, right? Because it is time dependent. There is a temporal, dependency of Hubble telescope. So at each time, it has to maneuver according to based on the time. There is a time dependency of Hubble telescope. So that can be continuous variables. So discrete variables can basically be solved using linear constraints. But for continuous, variables, we will have to look at the non-linear, constraints, but that can be undecidable because they may have infinite numbers. We cannot decide whether or not there is a solution for nonlinear or for continuous variables. Okay, we'll talk about the varieties of constraints too. Once again, please remember this slide. This is very important for your homework too. One can be unary constraint. Unary constraint that relates to only single variable, only just one variable. Now, suppose that Southern Australians, they really hate the color green. They really don't like it. They say, we're going to protest, if you assign us a green color, we're not going to like it. Okay, so what we do is we say Southern Australia does not equal to green. That means all the Southern Australians have protested the color green. We cannot assign the color green to Southern Australia. That's a unary constraint because it involves only one variable, right? Then we have binary constraints, which we have just seen a couple of slides before. Binary constraint that involves 2 variables. Then we have higher order constraints that involve 3 or more variables. For example, n by n queen. We have seen A, B, C, D, 1, 2, 3, 4, 5. So the constraint that involves 3 or more variables, those are higher order constraints. And then there are global constraints too that involve arbitrary number of variables. No, unary constraint that involves only one variable, binary, which involves two variables, and then higher order that involve three or more variables. The constraints, okay? The higher order constraint that involves three or more variables. All right. So, you know what? I think I'm going to skip just a few slides because I only have an hour left. All right. There are so many different real world problems that have been solved using constraint satisfaction problems, such as assignment problem. Who teaches what class? Okay. James and I discussed about the scheduling problem, if you remember. So come up with the computer science department, you know, an automated schedule, just run an algorithm. You have, you know, professors, right? Faculty with, you know, names, those are the variables. And then you can assign class times to each of the faculty. So those are the domains, right? But you have to basically satisfy all the constraints, such as, you know, one professor cannot teach two classes at the same time, right? One professor cannot teach two classes at a 15 minutes, you know, delay if the time taken from to go from one class to the other class is more than 15 minutes. So these were all the constraints that we have to follow. So that basically is the time, you know, assignment problems that was. I have about 90% of the code written. If any of you is interested in talking about that, just, you know, doing it as an independent study or something, do let me know. We can work on it. There's quite a bit of that part that is already done. So if you want to, you know, understand a little bit more about constraint satisfaction problems and actually solve a real world problem, then, you know, we already have the base that is created. So if any of you is interested, let me know, please. Which class is offered when and where? Hardware configuration, spreadsheet, transportation scheduling problems. A lot of the real world problems have been solved. Hardware configuration, what do we mean? Suppose that there is a car manufacturing, you know, company. So you basically have to I don't know what's going on with my pen. Okay, so what you do is in car manufacturing, what you do is something like this. You know, you have to build the axle before you install the wheels, right? Then basically you install the wheels in the car. Then basically you build the body, do the assembly, right? Wow, this car doesn't look like a real car, but so there's a you know, sequence, something like this. You do, you know, let's say task one, basically build the axle, right? Then install the wheels, then do the assembly. So each task takes like specific amount of time, like D1. This one takes D2. And you know, the constraints in this problem can be, you see here, task one, build the axle, right? That takes D1 amount of time, and T2, task two, installing the wheel, cannot start until these two tasks, until this task is done. That's one constraint, right? We can have T2 plus D2 has to be less than or equal to, yes, less than or equal to task three. So these are the constraints that you can have. So a car manufacturing problem can also be solved using constraint satisfaction problems. So far, so good? Is it making any sense? Yes? All right, so then let's get to the actual algorithm. Okay, so as I said that we assign a value to a variable and then see if it is satisfying all the constraints or not. If it doesn't, we backtrack, we go back. So it's a recursive algorithm. Sounds good? It's a recursive algorithm. We make one assignment, we assign a value to a variable, all right? And then we see that if it is satisfying all the constraints that we have. If it does, move forward. If it doesn't, go backward, which is why it's called backtracking search. Okay, it's a recursive algorithm. It's one assignment per variable at each step. Therefore, it's the depth first search. It's actually a depth first search. We will talk about it very soon. Something like this. You see, we start with Western Australia. We have the assignment, basically red, green, blue. And then we have Northern Territory. We have Southern Australia. As soon as we assign, let's say, the color red to Western Australia, our assignment basically will be left with only either green or blue for Northern Territory, because the red is not available for a Northern Territory anymore, right? So we take one step and then we move forward. And then we just, create, basically, we assign the values. It's a depth first search. What happens is you might make an assignment here somewhere that might violate the constraint when you go back up in here. Therefore, you will have to cancel that, backtrack, remove the value, backtrack, and do some other assignment that will satisfy all the constraints. So that's why you have to just go back. You keep backtracking. You backtrack quite a lot, which is why its time complexity is d to the power n. If there are n variables and if there is d domain, the time complexity is exponential. Bad, not too good. So here's an example. No, the start is basically when there is no assignment, right? So we have a completely empty, assignment. Empty variables, like we have a queue, we create a queue, and then within the queue, we put the assignments. Like the first assignment is Western Australia has been assigned the color green. Okay, great. Go forward. Next step. Now, Western Australia is assigned color green. Now assign color red to Northern Territory. Okay, put that in the queue. Go next step. At the next step, if there is a violation, what we do is we either remove Western Australia as a green from the queue and assign it something different, or we continue moving forward. So we have to continue going back and forth. Initially, every possible assignment is a suspect. Initially, everything is, the entire queue is empty. Something like this. You see, we start with an empty map. We can say Western Australia, we can assign it either red, green, or blue, right? So that's one assignment. We put that in the queue. All right, great. So here we have, if we have assigned basically, let's say I have red, I have green, this is the assignment. If we assigned it red, we have assigned it the value red. As soon as we get to the next state, for Northern Australia, our assignment is going to be reduced to only green or blue, right? Because we have assigned red already to Western Australia. Okay, keep going, keep going. At one point, you might assign some value to some of the variables here that might cause a problem all the way up there. So you have to go backtrack. Really tedious process, right? Something like this. Here's the algorithm. Okay. Let me just skip it for now. I'll get back to it. Okay. You don't have to implement this algorithm in Python code, which is why I'm just skipping it for now. All right. How can we improve it? Okay. So how can we improve? We can add ordering. We can add ordering. For example, we can answer questions like this. Which variables should be assigned next? Can we pick variables based on some order that might help us improve the backtracking? Okay. So we basically need to know what variable do we need to select next. In what order should its value be tried? So given the possible values that can be assigned, can we assign the values in some order that might help us improve the backtracking? Can we detect inevitable failure earlier? Can we do a little bit of planning? Can we do a little bit of pre-processing, right? So if we sit and plan a little bit earlier, then we can detect that we might have a failure in the future. Therefore, we shouldn't do this kind of assignment, right? Or can we exploit the problem structure? One way to improve backtracking is forward checking. Look at the next step. Okay, look at the next future step and see what, and look at what idea. Keep track of domains for unassigned variables and cross off bad options. Now you might be wondering, what does cross off bad option mean? Look at the second line. Cross off the values that violate a constraint when added to the existing assignment. Something like this. Now suppose that you start with an empty map, right? Everything is still running. Yeah. So you start with an empty map, you make an assignment, something like this. You assign the color red to Western Australia, right? So at that point, you say that you have assigned the value red to Western Australia and cross off the bad options. By crossing off the bad options mean that look at its adjacent states, Northern Territory and Southern Australia, right? If Western Australia is assigned the color red, then Southern Australia cannot be assigned the color red, and Northern Territory cannot be assigned the color red. So we have just removed from its domain. Remove this color. Okay, great. Then go forward. We have assigned the color green to, which state is it? Queensland. If we assign the color green to Queensland, then that means Northern Territory is not going to be able to have the green color. And Southern Australia also is not going to be able to have the green color. And then we have New South Wales, right? It can also not have the green color. So just cross out the bad option. Just look at the next step and cross out the bad option. So this is a really interesting applet that I also found online that actually solves this problem, precisely this problem. Uh-oh, don't run away. You see here? So if we do backtracking search, and if we go with the forward checking, now you see next. So it will start with Western Australia, somewhere here. It will assign the color blue, and then it has checked one step ahead. These three, assignments may have, like blue color. So it has just removed the blue color. It goes next. It just checks one step forward, right? Just checks one step forward. And then all what it does is, you see, as we play, it just continues. It still needs to do a little bit of backtrack, right? But it does find the solution better than backtrack, just the backtrack. So we have looked at just one step ahead. But there is still quite a bit of backtracking involved, still quite a bit of recursion involved. All right, how can we improve it even further? Something like it, like this, okay? So forward checking propagates information from assigned to unassigned variables, but doesn't provide early detection for all failures. Why don't we check the constraints, the arcs, the arrows that we have, and just look for all the possible arcs, and then just begin with that. So why don't we do constraint propagation? Okay, so something like this, and at this one point, so with forward checking, we get to this state, and we say that Northern Territory and Southern Australia cannot have the blue color. So you see here, Southern Australia and Northern Territory, they both have the blue color, and now we have violated the constraint using forward checking. So forward checking still involves some of the backtrack. Can we improve it? Yes, we can. Constraint propagation, reason from constraint to constraint instead of variable to variable. Okay, so how can we do that? Well, we first basically go with the single arc consistency. We look at each arc. So you see, we have different arcs, right? Because Western Australia has a connection with Northern Territory and Southern Australia. So Western Australia has an arc from WA to NT and WA to Southern Australia, right? So that's how we create a graph. So what does it mean to have an arc consistency? Let's read the definition. An arc from X to Y is consistent if, with double F, if and only if for every X in the tail, there is some Y in the head, which could be assigned without violating constraint. Does it make sense? Hopefully not, okay? Because I'm going to explain it. So from every, so you see here, X to Y arc. So just let's look at this arc. So we have assigned basically, let's say we have assigned red to western state. Now we have to look at this arc. Okay, so this is the tail. Remember, delete from the tail, not from the head. So this is the tail of the arc, and this is the head of the arc. So I'll tell you about like how to delete from the tail. So it says for every X in the tail, there is some Y in the head, which could be assigned without violating the constraint. So the constraint is still there. WA cannot be equal to NT. So if we assign the value blue to NT, if we assign the value blue to NT, are we violating a constraint? No, right? Because Western Australia can still have red. Perfect, fine. If we have assigned red in Western Australia, can we still assign green to Northern Territory? Yes, right? Perfect, great. We still haven't violated any constraint. If we assign red to Western Australia, can we assign red to Northern Territory? No, right? Now you delete from the tail. So meaning you have to delete this color from the tail. And then just look at for all the possible arcs. For all the possible arcs. Something like this. So you see, then you'll have to check this one too. So check all the possible arcs and enforce the consistency. Just remove values that basically violate any constraints and remove from where? Remove from the tail, not the head. You have to look at basically, you know, the tail variable at the tail. Ronald. Significance of the two. So if is if and only. That means it's a shorthand version of if and only if. Okay. So please remember this. Please remember this. This is remember delete from the tail, not from the head. If you start deleting from the head, you're gonna have problems. Okay. So if you look at the demo again, you have, let's say we do backtracking, and then we do arc consistency algorithm. And then you see next, if I assign any value here, am I doing MRE, none, filtering? What am I doing? 1 second. Next, yeah. So you see here, as soon as we assign the value here, it has checked the entire graph, all the arcs together. So it has actually done quite a bit of planning. It's still better, still not the most efficient algorithm out there to solve problems, but you see, it's not backtracking anymore. It just does some planning, but it's not backtracking that much as compared to forward checking. I'll tell you its complexity still, once again. So you have to check for each arc. Now you see here. So if we're looking at this arc, okay, we're looking at, you know, V and NSW. So suppose that we have removed one value. Suppose that we have removed the color red from V. We will have to go back and check all the arcs again between Southern Australia to V, between Queensland to Victoria, right? Between Northern Territory to Victoria, right? Because we have removed a value now that might have impacted the neighbors of V again. So we are actually doing it over and over and over for each variable. So if we are doing any deletion, any, you know, addition, we're going to have to go back to the neighbors of the variable again. So we look at all the arcs, but then we have to keep coming back to each arc again. You see here, if fx loses a value, neighbors of X need to be rechecked again, right? Because they will impact the assignments that may have been already made to the neighboring variables, correct? Does it make sense? So let me show you how basically its complexity is still not too bad compared to d to the power n. So now it's n squared dq. So let's look at the code if you want to understand how the heck this number has come from. Where has this number come from? Let's see, n squared dq. So you see at the top, while q is not empty, do this. So basically you're doing this for each pair of variables, right? So you're doing it like you're looking at one variable, right? And then you're looking at all its neighbors, you're looking at the domain, right? And if there is any deletion, you will have to come back to that variable again, right? You will have to look at that variable again because there might be another deletion somewhere, and from some connection, you'll have to get back to it. So you're doing it something over and over and over, right? Which is n squared right here, maximum n squared so far, okay? So what you're doing is you're doing something over and over. You remove that from the, from the queue. You remove the inconsistency here. We basically get to this loop, okay, for each domain. That's 1D, right? 1D. So this is something like this. So we are looking at xi, xj. This is one node, one variable, and another variable. And we're looking at this arc right now. What it says is for each x in domain of xi, of xj, okay? Xj is the head, right? So we are checking its entire domain, right? For each value in the domain for xj, see if any of the assignment in the domain of xi is impacted by that, if it's violating any constraint. So what we are doing is we're looking at this domain of xj, and we're looking at this domain, right? Xi, that's d squared. Make sense? That's d squared. So we have n squared, d squared. Now, if we have checked this, if there was a value that was deleted from xi, we will have to get back to xj again, the neighbor of xj, because we have deleted a value, right? So that's another d. We'll have to check its domain once again. That's another d, which is why it's n squared d cube possible. There are still ways to solve that using n squared d squared instead of d cube. I mean, for small numbers like 5 up to 10, it's simple, just like straightforward. But suppose that you have 100 by 100 queen problem. So using backtracking, by the way, we can solve 25 queen problems. 25, still not too big. Using arc consistency, we can go up to 100 queen problem. So we have improved quite a bit. We can go all the way up to 100 queen problems. All right. Now, remember that question we said that which variable should we select? Ordering, right? To improve backtracking, ordering. Okay, there are two different ways to select a variable. Minimum remaining values. Choose the variable with the fewest legal values left in its domain. The one that has the least number of values possible to be assigned. Any reason why? Sorry? Tightest constraint, exactly. So that is the variable that is going to cause the problem in the nearest future for you. So why don't you just, fix those and get them out of the way, right? This is one way. It's called MRV. Choose the variable with the fewest legal values left in its domain. There is another way, something like this. I think I don't know why I did this. Then least constraining value. Choose the one that rules out the fewest values in the remaining variables. Okay, that rules out the fewest values remaining in the fewest values in the remaining variable. In the remaining variables, just look at the ones that have the fewest values that are left instead of looking at its own. Okay. So I wanted to have a break to just have a minute break to just digest what we have already talked about. There is a quite big chunk of the homework 2. Basically, half of the homework 2 is based on solving a real world problem using constraint satisfaction problems, which is why I wanted everybody to be here, but there's still half the class. I think 17 people. So then people complain and say, oh, it's very difficult. It's hard. If you don't attend, if you're not in the class, it's definitely, as I mentioned in my first lecture. If you don't attend, if you don't participate, I promise you this course is going to seem extremely difficult. But if you are in the class, I mean, there are several faces that I see in every single lecture, and I really appreciate it. What? You said something that I missed it. But anyway, okay. So to once again improve in terms of the time and space complexity, we can solve it. We can decompose the problem. Once again, software engineering concepts. We can decompose the problem, right? We can take a really, really large, graph, right? Like Western Australia, Northern Territory. So these are just the nodes and the arcs. This is just exactly the map of Australia problem, right? So we can take a large graph and we can basically have a decomposition. We solve this first, then we solve this, then we solve this, and then we combine the results. And we have a CSV solution. Does this seem even possible, feasible? Decompose it. Decompose the problem. Does it even seem feasible to you by looking at the graph? Look. No, right? Because if you decompose it, where are these arcs going to go? There are connections. There are connections. So you have to, it's not going to be possible to just decompose it in a random way. You can still do it something like this. You can come up with a linear structure, or you can do something like this. Instead of looking at just decomposing it, you can do something like this. Let me show you this. Solve basically the CSP for the variable that has the highest number of connections. Okay, for example, Southern Australia. So solve, like remove a value or make an assignment to that variable. And once that is done, then get the rest of the tree as a linear structure, as just a linear tree. And then using the linear tree, what you can do is you can convert something like this. So suppose that you have this tree left. This tree left, just simply draw it in a nicer way, something like this. This is exactly the same tree, okay? Exactly the same tree, just draw it like that. What you do is just do it in 2 steps. You have some assignments, okay? You remove backward, okay? You remove the values backward, something like this. Start with F, okay? Start with F. If F is given value blue, then D is connected to it, right? Then remove D, remove blue from D. You see here, I've assigned value blue to F, then just simply remove the blue from D. Whichever node that is, it's in the tail. So we're just simply removing from the tail, right? Then we look at D, right? So D, if we assign basically, green to D, then there might be a violation. So we simply remove green from B because D has a connection with B, right? So we just remove green from B. So we are removing backwards. We're removing backwards like this. If we assign blue to B, then we cannot assign blue to A. So we simply remove blue from A. And then we assign forward. Then we assign the values forward. So you just do that in 2 steps now. You have the linear structure, you have solved for the one that has the most number of connections, then you have converted the tree into a linear structure, remove the values backward, and then assign the values forward. Just start with the left and assign the values forward. And that can improve the runtime to NB squared, which is much better. But you will see not a lot of real world problems can be converted into a linear structure. Okay, but the good thing with CSPs basically is that it has been applied and it can solve many, many real world problems. We are gonna talk about, well, your homework is going to be based on forward checking or consistency based on a real world problem that we are going to talk about, an example from a class perspective. So you will have to solve that problem by simply just removing values and assigning some values to the variables and identify basically, what unary constraints are that you can see in that problem, draw a constraint graph. So you will have a long statement by saying like, okay, here's the real world problem. You have to just solve this problem by doing some assignments, to some variables, and then draw a constraint graph from that statement. After you drew the constraint graphs, identify what are the unary and what are the binary constraints. If you are able to draw the constraint graph, you can look or see directly what unary and binary constraints are there. Binary constraints are if you have an arc between two nodes. That's a binary constraint because they both are dependent. Like Western Australia and Northern Territory, there was a binary constraint, right? So you will be able to identify unary and binary constraints from constraint satisfaction problem, and you will have to draw something like that on the left, and then you will identify, you will do something like this, the assignment of the colors, something like that, or assignment of the values that you might. So pretty interesting, topic that has been applied to several real world problems. I think in the next week, we're going to start talking about reinforcement learning. But before that, I might be able to show you a couple more examples of CSPs. And next week, I'm going to have to start making an announcement from now about the attendance from next week. It is going to, I think people will fail it if we don't attend at least 3 more weeks, at least, because this is going to be a very big part of the of the course. Markup decision processes. If we don't attend markup decision processes, I promise you will have no idea what reinforcement learning is, what Bayesian networks are, what probability is, how we are going to assign conditional probability, do the conditional probability, variable elimination, do the inference in Bayesian networks. All those, I promise you will miss it if you don't attend next week. So please, keep that in your schedule. And I'm going to start making announcements from now, because the rest of the people who have never seen, they're going to have a problem with this course, and they're going to start crying and saying that, this is really, really hard, which I don't want.